What's that? Oh, I am going to afterwards, but I already started this.
Where? I'm just floating right on.
Inside of it?
Yeah.
Oh, gross.
What is it? It's a piece of duct tape.
Somebody did that to you.
Did you crack it?
Yeah.
I just went and filled it up in the fountain, and then I took a drink.
Yeah, somebody stuck that in there. All right.
EP finals are at Marquette. Pretty gross. Imagine that could have been stuck to the ear.
Okay, in the last chapter, we talked about three distributions, the binomial, the Poisson, and the geometric. Now, from this chapter till the end of the book, we're going to be talking about the normal distribution.
Is it easier?
Yes, I'll go yes. Most of the data in the world, a lot of the data in the world is normally distributed. So what does it mean to be normally distributed?
Whole numbers.
5 things, not whole numbers. You get a normal distribution when your mean, median, and mode are all approximately the same value. And when that happens, you know this shape. It's the symmetrical shape. Where our mean, median, and mode are all on that line of symmetry. Okay, the interesting facts about this graph. First one, the total area under the curve, nice choice, equals 1.
I'm not barely passing this test.
That's, there you go.
You're huge and I cannot do this.
Which means you should move to the front of the room. Okay. The curve approaches. Remember this when you guys go to college next year. Everybody's got to move because Austin made one power move to the front. Needs like a big space to get around him.
Wow.
Okay, the curve approaches but never touches the x-axis. And the last thing, if you remember, the standard deviation indicates how spread out the values are. Oops.
Wait, spread out the what?
The data are.
Or not values?
Yeah, it doesn't matter. Values, data, same thing. So if you have a small standard deviation, everything's packed together, the graph is going to be really narrow. So a small standard deviation is going to give you a narrow graph. If you have a large standard deviation, it means they're way spread out, the graph is going to be really wide. Yep.
Matt. Don't worry.
Are you kidding me? I'll marry the beach on that 5 o'clock.
Come on now, focus.
Where is
Is this
this, everybody?
big?
Blood drive, I think.
How many lines?
Those are the blood drivers.
This is it. This is the biggest it's going to be. Let's see, this is graph A, this one's B, and then that one's C. Alright, so there's 3 different normal curves there. I tried to make them look normal, but they're not. the best. Mm-hmm. So what I want you to be able to do with these three graphs is tell me what the mean of each graph is, and then after that I want you to be able to rank the standard deviations from the smallest standard deviation to the highest standard deviation based on the shapes that are here. So, first question, what is the mean for each graph? What's the mean for A, B, and C? How do we know where the mean is at? The line of symmetry. So A and B, the line of symmetry is at 45, so the mean is 45. And for C, the mean is going to be at 60. Now, which one has the smallest standard deviation? Why C? It's the narrowest. The narrowest is the smallest standard deviation. All the data is packed together. So this is the lowest one. What's next? A is the next narrowest. And the biggest standard deviation is B because it's the one that's more spread out. Make sense? Easy. There. Not quite. Page 1 is done. Of about 4. All right. The empirical rule. The empirical rule approximates the area under the curve. And the three values that go with the empirical rule are 68, 95, and 99.7.
Wait, what?
I'll tell you. These three numbers are going to help us get the area under the curve, and it's all going to make sense here in a minute. Now this curve I'm going to make is quite large, so draw this big because we're going to be putting numbers inside of it. All right? So give yourself some space to do this. So we've got our normal curve. Our mean is right in the middle.
We just go across the whole page.
Yep. Because we're going to put numbers inside of it. Now what each of those numbers represents is if I move one standard deviation away from the mean, and then another one standard deviation, and then another one standard deviation, it's telling me what percent of my data is going to fall in that range. So what this 68 means is if I move one standard deviation away from the mean, that's above and below, 68% of my data is going to fall in that chunk. If I go out 2 standard deviations, 95% of my data. And then 3 standard deviations, 99.7% of my data is going to fall in between those two values. So in the way it works is kind of chunk it up about the same as mine. 1, 2, and they're all evenly spaced. The third one takes you way out to where it just gets really close to the x-axis. And then we do the same 3 symmetrical values on the other side. 1, 2, 3. So what each one of these divisions are they're one standard deviation apart. So this would be the mean plus 1 standard deviation. Next one's the mean plus 2 standard deviations. And then the mean plus 3 standard deviations. And when we go below the mean, we just subtract a standard deviation to get each one of those. So the mean minus 1 standard deviation, mean minus 2 standard deviations, Alright, so what the 68 represents is if I go one standard deviation away from the mean, that means one below to one above, 68% of your data is going to fall in there. And because it's symmetrical, that's telling me we've got 34% on each side here. If we go out to those two standard deviations away from the mean, so from this value all the way over to this value, those four chunks together are going to house 95% of our data. So that's all four pieces. So if I take 95 and subtract 68 and divide evenly, you'll get 13.5% for each of these chunks. So those four add up to 95%. And then our 99.7, if we go 3 standard deviations away from the mean, that's below to above. So those 6 chunks of my graph are going to add up to 99.7% of our data. So if we take the 99.7, subtract off the 95, divide evenly, 2.35%. So does data ever get beyond those into the tail pieces?
No.
Absolutely.
No.
3/10 of it, not much, but there's some people out there, there's data out there, not people, could be people. If you do the math here, it's going to be 0.15%. Okay, so did you know that IQ scores are normally distributed? Not very big. I'm going to fit it right here. Oh, 5 lines maybe? IQ scores are normally distributed. The mean IQ score is 100. With standard deviation of 15. Can you find the probability of selecting a person and I'm going to ask some questions. So, first thing I told you was that IQ scores are normally distributed. I'm going to draw the graph so we can answer our questions. So this does not have to be very big. The average IQ score is 100. And the standard deviation is 15. That means when I go 3 standard deviations above and 3 standard deviations below, 99.7% of our population is going to fall in between those two values. So we got those really genius people that are up here in the tail pieces. They do exist. I don't think we're sitting among anybody with that IQ, but that's okay too. So, to find these values, we're just going to add the standard deviation on a 15. So this first one here would be a 115 IQ. Add 15 again, we'll be at 130. And 145. That was a good question. I will Google that afterwards. We asked that and then I forgot to look at it. Somebody said 220. But I didn't look at it after we were done. Remind me when we're done, I'll see what the highest recorded IQ score.
No.
What they did say, Bill Clinton had an IQ score of 190.
Bill Clinton.
That's what James Jandro claims. I don't know. He's into the government stuff. I'm thinking he's probably right. Okay. 85, 70, and 55. So subtract 15 to get each one of those.
That's all we were doing so?
Yeah, nope, now the question. Okay, so if I randomly pick a person, what is the probability that the person I select has an IQ score between 85 and 115? So the probability is going to match the area on the curve. So if you look, I picked something easy to start with. 85 is one standard deviation below to 115, that's one above. It's these two sections of the graph. So what percent of my people land in here? 68%. So you can write 68% or 0.68, I don't care.
Is that the same on every graph?
Yes. If it's normally distributed, this rule applies. Okay, what's the probability your person has between a 55 and 85 IQ score? So all we're doing is adding the chunks of the graph from the top part that we did there. So where is 55 to 85? What parts do I need to add together? So, yeah, so it's going to add those two together. So if I do decimals, that's 0.0235 plus 0.135, and we get point.
How do you get 0.68 out?
Oh, 85 to 115. See where they're at?
Yep.
It's one below to one above. So now I go up to this graph, one below to one above. So the answers are up here. I just got to see what's matching. So 55 to 85. Take a look, Austin. There's 55 to 85. It's those bottom two chunks. Got it?
Okay.
And last one, what about picking someone over 130? What's that probability? Yeah, it'd be 15%. Or 0.15 as a decimal, your choice. How about over 130? What pieces do you have to add together? You see it? Are you just being quiet? Just be quiet. Yep, so the 2.35 plus the 0.15%. And if I stick with my decimal, it's going to give me, I'll go 0.0235. To the decimal? It doesn't matter to me what you do, but I think the book does all decimals. But I wouldn't mark a percent wrong. 0.025, so 2.5%. Okay, so you can do the empirical rule. Alright. And the last thing in section 1, but we're not done, because we're going to go into section 2. Because we can. We're going to estimate the mean and standard deviation. .9 or 0.1. That's all I'm going to give you. Oh boy. And we're assuming those are symmetrical. That's the best thing we can do here. So where's the mean going to be at? And how do I find it? Symmetrical. The mean's right here. How do I find this value? There you go. You're going to average those two outside points. 2.9. Look at what moving to the front does for you. Divide by 2. So our average is 3.5. All right. So now to figure out the standard deviation, what we're going to have to do is assume that that 2.9 and that 4.1, those are my values that are 3 standard deviations away from the mean. That's the assumption we're going to have to make in order to do this. So what I can do is look at the mean to this farthest out value and divide that into 3 equal chunks, and then see what that standard deviation should be. Does that make sense? So I want to take this distance right here and divide it into 3 pieces. Well, how do I get this distance? 4.1 minus 3.5. Then divide that into 3 chunks. And then we'll see if it works. 4.1 minus 3.5. divided by 3. Anybody? What you got? 0.2. And let's see if it works. If I add 0.2, 0.2, 0.2, I better land at 4.1. Let's check. Adding 0.2, that would give me 3.7. Adding 0.2, 3.9. Oh, look at that. Would you look at that? So we got the mean and standard deviation just using some common sense. Alright, that's all that's in 5.1.
We stop.
How you got 3.7,
Added 0.2. Remember we add a standard deviation to get to each? Yep. Okay. If you want to start a new page, go ahead and start a new page. It's a new section. I'm not going to waste my paper here.
Like, as if we would be doing it tomorrow.
Yeah. But it's, we're just going to get a start on 5.2.
She kept saying, foot, dirt, bad.
Standard score is a z-score. Indicates how many standard deviations away from the mean that a value is. So I want to go back to our IQ score real quick, just to talk about what I'm saying here. So, if I looked at, say I had an IQ score of 115, my z-score would be positive 1, because I'm exactly 1 standard deviation above the mean. If my IQ score was 70, my z-score would be negative 2, because I'm exactly 2 standard deviations below the mean. So it's how many standard deviations away from the mean that a value is. Well, is every single piece of data going to land on 1, 2, 3, negative 1, negative 2, negative 3? Probably not. Of course, their life is not going to be that easy. So, we've got a little formula. The z-score for an x value. So you first want to find how far away from the mean it is by taking the x value and subtracting the mean. You take that distance, and then you see how many standard deviations fit into it. So you divide by the standard deviation. Simple formula. Okay, utility bills. Are normally distributed. With a mean of $70 and standard deviation $8. Now I'm going to ask you to convert some utility bills into a z-score. So I like to make the graph. Keeps my head straight about what's going on and what I'm finding. So the mean is 70. And if I add 8, 78 is 1 standard deviation above the mean. That would have a z-score of 1. If I add 8 again, I'm at 86. That would have a z-score equal to 2. And then add 8 again, we're at 94. That has a z-score of 3. Subtracting 8, that's 62. That's a z-score of negative 1. Subtract 8, we're at 54. That's a z-score of negative 2. And then one more time, 46. Z-score is negative 3. What's a 70? What's the z-score for 70? 0. It's right on the mean. Okay. So, tell me, a utility bill of $84 what z-score would it have? Well, just estimating, it should be between 1 and 2, so 1 point something.
The 1 point.
Probably like 8.
Let's see. We're just going to plug into our formula. So it's 84 minus the mean. Our mean was 70. And then we divide by 8. And z-scores go out 2 places. And you'll see that in a minute when we start reading the z-score table. Anybody? $1.75. So 1 3/4.
1.8.
You were a good estimator. $50 is down here. Should be negative 2 point something. So 50 minus 70 divided by 8. That's negative 20 divided by 8 is negative 2.5. Okay. So you can convert values to z-scores and know what it means. All right, the last thing we're doing today is finding the area under the normal curve. We just found area for 1 standard deviation away, 2 and 3, but what about stuff that's in between those? And we've got a big table. And you will use this table from now till we're done in June. Okay, I copied the table. It's also on the front cover of your book, and it's in the back of your book. So if you lose this, I do have extras for later, but it'll be handy for homework later.
Late Christmas.
You're probably gonna lose it.
Yeah, late Christmas present.
Or what is this?
The table you need to learn how to use. So we will use it from now till June, well, May when you graduate. Maybe if you graduate past the class.
Actually, that doesn't, but very much the class doesn't matter.
It doesn't matter? You got 4 credits in math, you don't need this one?
No, if I pass personal finance.
If you pass personal finance.
You got any more? You got any more of those, bud?
Oh, I don't need one.
What?
What? I don't have one. 58.
Record that you got it. Oh, yeah. Want that?
Yep.
Sorry.
Hey, I'm doing all the homework, it's just a test server.
Okay, let's take a look at this. What this graph, or this table is giving us. If you look down the vertical column, it's got a z-score here. On one side they're positive, one side they're negative. So what the, on the left-hand column, it's giving you the z-score out to the tens place. So like 1.4. But then across the top, it's got the hundredths place. So if I wanted to look up 1.45, I'd go to 1.4, then I'd go to the 0.5. Okay, now what does this number represent? It's giving me, yes?
Why is the negative 0.0 different than the positive 0.0?
It should be 0.5.
The first one's the same as this.
Yeah, because that's the only place where it's the same.
Other than
Negative 0.0 is the same as positive 0.0. They're the same value. It's not. They're the same spot. Opposite of 0 and positive 0, same thing.
Oh, that actually.
So that's the only value that's going to be the same. Now, what this number is telling me, let me go back to my 1.45 that I had. This 0.9265, that's telling me if I was at a z-score of 1.45, say it was right here, this 0.9265 is the area behind me. It's how much of the graph is behind you. So that's why they have it shaded to the left. So the table entry for z, that means every single one of these numbers, is it's the area under the curve to the left. So think behind. So by the time we do 4 of these, you should understand what these numbers represent. Are you ready? It will in a minute. Here we go.
Wait a minute.
Sample 2.
What's the bold?
I will show you. Find the area. And our first one, I want you to tell me how much area is to the left of z equals negative 1.63. I first want you to sketch this. So sketch a normal curve. Where's the 0 z-score at again? Right down the middle. So a negative 1.6, and you're just estimating, say about here. This is negative 1.63, my best estimate of it. And I'm asking for how much area is there to the left of it, all of this back here into the tail. Well, if I want the area behind something, all I've got to do is look up this z-score on the table. So, Austin, take your table, flip it over to the negative z-scores, look for negative 1.6.
Where?
Down the column, go all the way down, find negative 1.6.
Okay.
Now go over, look at the top, go to the 0.03.
Alright,
Because we want negative 1.63.
oh, I found a number.
So how much area is behind it?
0.05.
0.0516. So just over 5% of the graph is shaded behind it. So 0.0516. Zoe, good? Everybody good?
Yep.
So this area is 0.0516. So that's a little over 5% of the graph that's shaded. Try one more to the left before I challenge you. To the left of z equals 2.88. Make me a sketch first. Should this number be a high area or a low area? Pretty low, he said. Where is 2.88 at? It'd be way out here to the right, almost 3 standard deviations out. And I want the area to the left of it, so I'm looking for all this. It's an estimate. Just know that 3 hits right about here where it starts to tail down. So, remember it's only 1, 2, and 3 out to the where it really gets close. This, I have most of the graph shaded. This better be a high area. So, look up 2.8, oh, 88. 2.88. So go to the positive side. 2.88 is all the way over here. 0.9980.
Yeah.
So 99.8% of the graph is shaded. 0.9980. Okay. So do we understand what that number on the table is giving us? The area behind. Now, if I ask for the area to the right of a z-score, say 1.25. If we sketch it first, oh, that one's supposed to touch. There's 0. 1.25, I'm going to say about here. Doesn't really matter. And I want to know the area to the right. Well, when we look up the table value of 1.25, what area is that going to be giving me? The area back here. Well, what do we know about the total area under the curve again? Adds up to 1. So what are we going to do? 1 minus whatever the table gives us, because it's going to give me the area back here. So it's going to be 1 minus. So what is the area behind 1.25? 8944. So it's going to be 1 minus 0.8944, because that's what this is here, 8944. So what does that come up to be? I did a different 1 second hour. 0.1056.
Yeah.
Okay.
We're done.
No, I got one more thing I can ask you. Then we'll be done. So we can go left, we can go right, we can go in between. Between. Let's go z-score of 0.92 and a z-score of 1.73. So if I sketch that first, Here's 0. A 0.92 z-score is just shy of 1 above the mean. Just a smidge shy of 1. I'll call it right there. And then 1.73 about there. Probably overshot that a little bit. And we're looking for in between. Okay, so when we look up 1.73, I want to shade what it's going to give you. When you look up 1.73, it's going to give you the total area behind it. All of that. When you look up 0.92, it's going to give you the area behind that. So Alex, what do we got to do with those two numbers? Just subtract them and it'll leave you with the chunk right here. So, 1.73, what's the area there? 9582. And then what's behind 0.92? 8212. And then it's just subtract.
1.137.
0? If you want a 0 there? Okay.
So we subtract
Right, honey,
Yep.
from the right from the...
Yes, because that's going to have the most area behind it. Because area is always going to stay positive.
Are you gonna check the review or something?
I am going to check the review.
Damn.
Alright, me and Amber did it.
You took up all the time.
We're all gonna get pizza.
Come on. And they got content.
Monday. Oh,